Hello everyone, my name is Ananya, and this is the first in a series of 15 calculus video lectures. So here's a brief overview of what we're planning to cover in this class. Today we'll start out by covering the definitions of limits and continuous functions, and then in the next few lectures we'll spend some time talking about derivatives and integrals, as well as various techniques to compute them. Then we'll look at how derivatives and integrals are related through the fundamental theorem of calculus, and finally we'll look at various applications of them. So before we get started, I just want to take a quick look at where we're headed with this course. So say we have any function, let's call it f, and we can draw a graph that looks something like this. Then for any fixed point on the graph of the function, we can draw what's called a tangent line. And that's just a line that's parallel to the graph at the point. So that's going to look like this. We can then find the slope of this line, and the slope of the tangent line at some point is what's called the derivative of f at that point. And then the other thing we can do is if we have any 2 points in the domain of the function, we can look at the area underneath the curve between those 2 points. So that's the area of this region. And that's called the integral of f between these 2 points. And the notation for that is this integral symbol from a to b of f of x dx. And the goal of this course is to learn how to find these, as well as to learn how they're related to each other. So today we'll get started with something that's very important. This is the concept of limits and continuous functions. So the first thing we want to do here is define a continuous function. And this definition is not going to be the most precise, but once we define limits later on today, we'll wrap back around and formally define continuous functions. But for now, here's the general definition. So we say that a function f is continuous on some interval ab, and this doesn't necessarily have to be a closed interval, but I'm just writing it this way, provided that it's defined at every point in this interval. And provided that it has no breaks. So we haven't formally defined what a break is, but you can get an intuitive idea by looking at these pictures. So for example, this first picture is continuous on AB because it's just a smooth line and there aren't any breaks in the function. While this one, on the other hand, this has this break at the point B. So what this picture means is that the function is defined to be whatever points on the curve away from B. But at B, this is the value of the function, not this point here. And so this function is said to have a discontinuity at B. And that just means that it's not continuous at B. B is the point where the break occurs. However, this does mean that the function is not continuous on the interval from A to C because B is inside that interval. But because there's only this one discontinuity at B, it is possible to narrow down the interval so that the function is continuous on some smaller interval. And in fact, if we say pick our interval to be this, from A to B, but not including B, or from from B to C, again, not including B, then the function is continuous on both of these. And the other thing to note here is that this discontinuity is what's called removable. So what it means for a discontinuity to be removable is that we can fix the discontinuity and like make the function continuous by changing the value at this one point. So here we could, instead of defining the value at B to be this point, we could just get rid of that and define it to be this point here. And that would make the function continuous. So this is called removable. And there are some discontinuities that are not removable. So let's practice with a few examples. Let's just do one more example first of a function that has a non-removable discontinuity. So here's another function that's not continuous on the interval from A to C, and that's because it has this break at B. But here you can see that there's no way we can fill in the point at B. If we put it here, then it doesn't line up with this point. But if we put it here, it doesn't line up with this point. And so this is what's called a non-removable discontinuity at B. And again, the function is continuous on this half open interval from A to B or on the half open interval from B to C, but it's not continuous from A to C. So now let's do a few examples for practice. Here are 5 graphs. Feel free to pause the video for a second and try to figure out which of these are continuous, and if they're discontinuous, what kind of discontinuity they have. All right, so let's go through the answers real quick. So for this first graph, this is discontinuous. And the reason is this is discontinuous is because of this point over here, because it has a break and the value of the function at this point does not match what it should be on the line. So this is an example of a removable discontinuity because we could just get rid of this and fill it in. Now the second graph is continuous. There aren't any breaks and we can like pick our interval from A to B like that, and it's just a nice smooth curve, and that's continuous. All right, the third graph is not continuous because it has this discontinuity at the point A. This is in fact not even defined at the point A. So a function can never be continuous at a point where it's not defined. So it's automatically not continuous at A. And it's also not a removable discontinuity because there's no point we could fill it in where it actually meets the graph. That's because the graph is going off to infinity when it gets closer to A. It's the same deal here for the fourth one because this is going off, well, it's going off to negative infinity from this side and infinity from this side. But again, it's not defined at B, so it can't be continuous at B. And finally, this graph, the last one, is not at all defined at this point here. So it's not continuous at this point. However, it is continuous on the interval from A to B because this point's outside that interval. So this part of the graph from A to B is completely smooth. And so this is continuous from A to B. So just to summarize, the first one's not continuous. The second one is continuous. The third one's not continuous. The fourth one's not continuous. And the fifth one is continuous from A to B. But it does have a discontinuity outside that interval. So now the next thing we want to talk about is the concept of a limit. So when the graph of a function approaches some point, so we're getting closer and closer to some point in the domain, we can look at what the value of the function is approaching. So for example, if we go back to this previous example, even if a function is not defined at a point, let's call this point A, even though the function is not defined at A, we can look at what the value of the function, or if it's not continuous at a, we can look at what the value of the function is getting closer to as we get closer to a. And this value is called the limit. And we would usually just write this as lim as x approaches a of the function f of x. And that's going to be equal to this value, even though that's not the value of a at the point, of f of a at the point. So the other thing limits allow us to do is talk about when a function is increasing without bound, when it's going off to infinity. And we can also use what's called an infinite limit for that. So here, as we get closer and closer to a, the function is increasing, and we can see that it goes off to infinity. It doesn't stop at any finite value. And so what we write here is that the limit of this function, let's call it f, as x approaches a, is infinity. And the notation we would use for this is limit, so lim. Underneath that, we'll write the value that x is approaching, so x goes to a, of the function, so that's f of x, and we say that that equals infinity. Now, in the previous example, we had x approach a specific value a, but that's not the only kind of limit we can take. So the other thing we can do is take a limit as x goes to infinity. And we could also do minus infinity. So the limit as x goes to infinity of f of x, and now I'm using this function here. So this is our f now. That's going to be the value that the function approaches as you go further and further right. So it's not completely obvious, perhaps, but we can guess looking at the graph that this is getting closer and closer to the x-axis as you go right. And so this limit here would be 0. All right. The next thing we can also talk about is what's called a left and right hand side limit. So in the previous example, we were taking what's called a total limit. So we're having x go to a, and we want it to approach the same value from both sides. So in this one, it's going to a from both sides, and on both sides, the function is going off to infinity. But it might not do that. In general, it could do different things on both sides of some value. And so this is where the left and right hand side limits come into play. So if we have a function that looks like this, then from the left side, as we get closer and closer to 2, the function value is approaching 3. All right, so then we would say that the left-hand limit of the function as x approaches 2 is equal to 3. Meanwhile, if we do the same thing on the right-hand side, then we're approaching from this side. Well, then it's approaching this point, which is 4. So in fact, the left and right-hand side limits can be different. Now, let's quickly talk about the notation for this. So for a left-hand limit, we're again going to do the limit as x approaches 2, but then we put a little minus sign up here. And that's because the left-hand side can be thought of as like the negative side, the stuff that's less than 2. And so we have this little minus sign, and then we can have our f of x, and that equals 3. And for the right-hand side, we do the exact same thing, but with a plus sign. And that's going to be equal to 4. Now, here's the really nice thing. If we ask about the limit as x goes to 2 without any left or right hand side limits, so we just do the limit as x goes to 2 of f of x, this exists if and only if the left and right hand side limits both exist, and if they're the same. So since these limits are different, the limit as x goes to 2 of f of x does not exist, and so we will just write d and e. And if these limits were the same, then the limit as x goes to 2 would just be equal to that same value. So let's practice. Let's do this problem for practice. Feel free to pause the video. I'll wait for a few seconds before giving the answer. All right, so we have our graph here, and we can see that the function, it has this asymptote at -1, and then it goes to this point 1, 1, where it has this jump discontinuity. Then it jumps to 2. We've got this nice curve going from the point 1, 2 to the point 3, 1. Then it jumps again, and then we have a line going from the point 3, 2, and it's just going outwards. So the question is asking us for the left and right-hand side limits as the function approaches 3 and as the function approaches 1. So let's work that out. So first we're looking at the right-hand side limit as x approaches 3. So now we're going to look at this value. So that's just this point here, and that's going to be equal to 2. Now we can also look at the left-hand side limit as x approaches 3. So now we're looking at it this way. And now we're headed towards this point. And that point is going to have a y value of 1. So the left-hand limit is 1. Then it's asking us to do the same thing at the point 1. So first it's asking for the left-hand side limit, because this is a 1 minus. So we'll look at it this way, coming in from the left. And that leads us to this point here, 1, 1. So the limit from the left as x approaches 1 is 1. And finally, it asks us for the limit as x approaches 1 from the right. And then we come in this way, and that leads us to this point here. And so that's going to be equal to 2. Now, looking at these, we can also ask, what's the limit? Just the plain limit as x approaches 3 or as x approaches 1. Well, as x approaches 3, the left and right-hand side limits are different, and that means it does not exist. And in fact, the same is true for the limit as x approaches 1. And that's because, again, this the left-hand limit is 1, and the right-hand limit is 2. And since they're not the same, the limit cannot exist. All right. We have 2 more practice problems now. So I'm just going to pause for a second here and let you think about the problem, and I'll give the answer in a couple of seconds again. So we've got this hyperbola, and we've got 2 parts, and this asymptote is at 3. All right, so the goal is to find the left and right-hand side limits as x approaches 3 of this function, and to find the total limit if it exists. So as x approaches 3 from the left, well, then we're looking at this stretch of the function. So this is going up, and we've been told that this is an asymptote, so this is going to plus infinity, or you can just write infinity. Now from the right, well, this is going down, and so this is going to be decreasing without bound, and so this limit from the right side, that's going to be equal to minus infinity. And then because these limits are not the same, the limit as x goes to 3 of f of x does not exist. And so we write DNE. And one more question we can ask here, what's the limit as x goes to infinity of f of x? Well, now we're looking at the function value as we go off to the right, as x goes off to the right. And well, it looks like this is getting closer and closer to the x-axis, so we can guess that this limit is equal to 0. All right, we have one more practice problem now, and then we're going to wrap around to defining continuity formally using the definition of limits. So here's the problem. And again, I'll just pause for a second and then we'll do the problem together. So we're given this function g of x. Just remember, we can use any letter for the name of the function. It doesn't always have to be f, though f, g, and h are the most common. So the question is asking you to graph this function first, and then find the limit as x goes to 1 from the left and from the right. Okay, so let's start by graphing this function. So I drew a graph ahead of time, so this is a little bit easier. So we can just label the graph real quick. I need a little bit more space there. Okay, so now we're told that g of x is equal to 3 when x is greater than or equal to 1. So when x is at least 1, and this is 1 over here, then we're going to be defining g of x to be equal to 3. And remember, because this is greater than or equal to 1, the value of g of x at 1 is also equal to 3, and that's why we close this dot, so it's filled in. And then the other thing we're told is that when x is less than 1, g of x is equal to minus 3. And then we draw the graph at minus 3, again going from this point. But keep in mind that over here we use an open circle, because it's not equal to minus 3 at 1. All right, so this is our graph. And now the question is, what are the left and right-hand side limits as x approaches 1? Well, as x approaches 1 from the left, we're following this line. So we're headed towards this point, which is going to give us a value of minus 3. And as x approaches 1 from the right, well, now we're following this line. And so that's going to give us a value of 3. And again, because these values are different, this tells us that the limit as x approaches 1 of g of x does not exist. All right. And finally, now that we know what a limit is, we can more precisely define continuity. So we first want to define continuity at a point. So f is continuous at a, at some point a. All right, so a is just any point, provided that firstly f has to be defined at a. Secondly, the limit as x approaches a of f has to be defined. And finally, these have to match. And what I mean by match is that the limit as x goes to a of f of x, that has to be equal to the value of f at a. So that has to be equal to f of a. And if these three hold, then f is continuous at a. And then the way we defined this earlier, we were looking at continuity on some intervals. So f is continuous on an interval from a to b. If it's continuous at every point in the interval. So until now, we've mostly been working with graphs of functions, but more commonly what you'll see as you go on and we learn about derivatives and integrals is equations for functions. And so we still do the same thing, But now instead of writing f of x and having some graph of f of x, we can actually write down some expression in terms of x. So it's super important to know certain very common examples of functions which are always continuous. So let me just write down a few of these. So firstly, any polynomial is always continuous. On all of R. In addition to this, the sine and cosine functions are always continuous, again on all of R. And tangent is continuous wherever it's defined. So not at the asymptotes, but everywhere else. The square root and in general, the radical function and nth root function, those are continuous on the positive numbers. Any exponential function where the base is a positive real number is continuous on all of R. So that would be y equals a to the x for a greater than 0. And in particular, a very common example is y equals e to the x, which is always continuous. And finally, the logarithm function, log x or ln x or any other base. Those are continuous on the positive numbers, this time not including 0, because you can't take a log of 0. But on the open interval from 0 to infinity, these are continuous. And once we have continuous functions, we can also use these to create more continuous functions. So firstly, if f of x is continuous on some interval, then any constant multiple of f of x is also continuous. And that's for any real number k. We can multiply f of x by k and still get a continuous function. If we have two continuous functions, continuous on the same interval, let's call them f and g. Then, so are the following. F of x plus g of x is continuous. You can always add continuous functions. F of x minus g of x is also always going to be continuous. And finally, f of x times g of x. So adding, subtracting, and multiplying continuous functions is always going to give you another continuous function. Now, we can also divide, but this requires one additional condition because we can never divide by 0. So f of x over g of x is continuous if g of x is never 0 on the interval. All right, and that's super important. We're never allowed to divide by 0. So if g of x were 0, we would have a point where this wasn't defined at all, and then it wouldn't be continuous. All right, and finally, we can get a composition of functions. So this is slightly different because we're not going to require that f and g are continuous on the same interval, but if f is continuous, on some interval, and g is continuous on the image or range of f. So that's all the values that f of x takes on. I'm using IMF to write the image of f. Then g composed with f, so we write that as g and then a small circle and then f, is continuous on the same domain that f was continuous on. And remember that a function is continuous if it's defined at a point and the limit as you approach that point exists and is equal to the value of the function. So if we know that a function is one of these functions on the list of continuous functions, and we're asked what's the limit of the function, you can just substitute directly because we know that the function is continuous. So let's quickly do an example. Say I ask, what is the limit as x goes to 2 of x squared plus 2x plus 1? Well, this function here is a polynomial. So we already know from what we just said that this is continuous. And what that means is that the limit as x goes to 2 of this function has to be equal to x squared plus 2x plus 1 when x is 2. And so we can just substitute that, and so the limit will have to be equal to 2 squared plus 2 times 2 plus 1. And I believe that that's equal to 9. Here's one slightly harder example that still uses the same concepts, but isn't going to be a function that's continuous everywhere. So remember that when we defined a limit, the limit only cares about the value of the function close to the point we're looking at, but not actually at the point. It does not matter what the function is defined to be at that particular point. So, for example, if we had a graph that looked like this, then at this point, say that's A, and say this is B, we would still say that the limit as x goes to A of f of x is equal to B, even though the value at A is not equal to B. So let's try this example out. So the first thing to notice is that this function that I've given you is not defined at 1, because at 1, x minus 1 is 0, and we can never divide by 0. But this function will be continuous away from 1. Anywhere that's not 1, this is not 0. And then the numerator and denominator are both polynomials, which are continuous. And so this is continuous. So let's write this down. When x is not 1, because when x is 1, it's not defined, then we can factor this. So x squared minus 1 is x plus 1 times x minus 1. And because we're assuming that x is not equal to 1, we can cancel. So the x minus 1 cancels, and this is just equal to x plus 1. And this is continuous away from 1. So to find the limit, we can now just substitute x equal to 1 into this. And so this limit is going to be equal to 1 plus 1, which is 1. Let's try one more example. So let's find the limit as x goes to 2 of x squared plus x minus 6 over x minus 2. And I'll stop talking for a moment so you can pause the video and try to figure it out. and I'll give the answer in a few seconds. All right, so again, we repeat the same trick. So we only care about the value of this function when x is not 2. So away from 2, the denominator is not going to be 0. And so we can write down what this is equal to when x is not 2. Again, we can factor the numerator. So this is equal to x plus 3 times x minus 2 over x minus 2. And then again, the x minus 2 cancels, and it's just x plus 3. So since this is equal to x plus 3 away from 2, and it's continuous, x plus 3 is continuous, we can just substitute directly. So the limit is equal to x plus 3 when x is 2. So that's 2 plus 3, which is 5. And that's a very good general technique for finding such a limit when it doesn't exist at the point, but it's well-defined everywhere around the point. All right, so let's do one last example before finishing for today. So this is going to be an example of a piecewise defined function. And now we're going to look at the left and right-hand side limits. All right, so we have a function that's defined two different ways, if x is greater than or equal to 1, and if x is less than 1. So this is not going to be continuous at 1 because there's going to be this break, but it's continuous everywhere else. Now the question is, what are these limits? So we're going to look at the limit as x approaches 1 from the left. The limit as x approaches 1 from the right. And the total limit if it exists. Well, to find the limit as x approaches 1 from the left, we only have to care about the value of the function to the left of 1, so when x is less than 1. So then it's just going to be equal to x. And since x on its own is a polynomial that's continuous, and we would just substitute, and so that's just equal to 1, because x is 1. And if we approach it from the right, well, in that case, we only care about this part of the definition, because we only need to look at the value when x is greater than 1. And then this is equal to x plus 2. And since x plus 2 is also a polynomial, we again just substitute. So we plug in x equal to 1 into this. And so that's equal to 1 plus 2, which is 3. And of course, since these two are different, the limit as x goes to 1 of g of x does not exist. So we just again write dne. So that's it for today. And next time we'll start with a review of some trig identities, and then we'll talk more about ways to find limits.